All right, so today we're going to look at how to determine the point of inflection, which is also going to help us describe what we call the concavity. And the concavity is like the curvature of a particular function. So without further ado, there's two different types of concavity. So we have concave up and we have concave down. So I have a graph of y equals sine x right here. If something is up, when we look at the word or think of the word up, it's pointing up towards the sky. So when we look at the section of the sine curve that is concave up, it would be the areas down below. So right here, this would be concave up. This would also be concave up. And you'll notice that means that the second derivative is greater than 0, and we will have a minimum. So the tangent, if we were to draw the tangent, so if I go over to the curve, if we were to draw the tangents, it's below the curve. Okay, so below the curve. So here would be an example. That tangent there is pretty bad, but you get the idea. Now, if we were to look at concave down, so that means that it's like a frown. So if you think of your face, if you're frowning, your lips are going to be pointing downwards. Same thing when we're talking about concave down. So the tangents are going to be on top of the curve. So right here where I'm drawing these tangents, oh wow, that's a really bad tangent. These tangents, we're going to have straight lines right here. They're on top of the curve or above the curve. Anytime you have something that's concave down, the second derivative is less than 0, and then we know that we have some sort of maximum value that's occurring there, either local or absolute. So in the situation for the sine curve, these are absolute minimums and maximums. So what is that going to look like as we go a little bit further? All right. So right here, we have a curve, y equals x cubed. Right at this point right here, we call that a point of inflection. If we find the first derivative, so y prime equals 3x squared, and then if I find my second derivative, y is equal to 6x, if I set it equal to 0, so 0 equals 6x, I know that x has a value of 0. If we were to do the same thing with the first derivative, 0 is equal to 3x squared. 0 is also equal to x. So in the first two lessons, we kind of looked at if you get a value from the first derivative, it tells you that it's a critical point. If you were to do an interval table here with this x equals 0, you'll see that the function is always increasing because we have y equals 3x squared for the first derivative. So if we were to draw that on our graph, y equals 3x squared, it's a parabola that's going to be roughly like this. Okay. Now, secondly, when we look at our second derivative, we see that we have a point right here. So this point right here, it's changing its concavity. So before 0, we would say that it's concave down, and then after 0, we say that it's concave up. So it's a critical point. It's not a minimum or a maximum, but in this case, because it's the same value from the first derivative and the second derivative, we call it a point of inflection. So the graph, there's something happening there. When that second derivative has a value of 0, it's inflecting. If I pop back to our sine curves, if you'll notice right here on the axes, this is where we're having that inflection happening because it's going from concave down prior to this value and then switching to concave up. So that point is the point of inflection where the curvature changes. Now, when we're determining this point, we can do something that's called the second derivative test. So what this is telling us is that if the first derivative has a value of 0 and you sub it into the second derivative expression, if you get a value greater than 0, it means that it's concave up. And if it's concave up, that means it's a minimum. If you take that 0 and you substitute into the second derivative and it's less than 0, that means it's concave down. So if it's concave down and has curvature that's down, then we say that that's a local maximum. Now let's say we find that value where it equals 0. If you substitute it in and it also equals 0 for the second derivative, then the point of inflection is going to win. So if you find a critical point in the first derivative and you get the same value in the second derivative, it will not be a minimum or maximum, but it will be a point of inflection. So that's what this notation is saying right here. Now, so typical question, find the point of inflection for y equals negative x cubed plus 6x squared minus 15x. Okay, so our first step, we're going to find the first derivative. So we get negative 3x squared plus, whoops, not 6. Oh, okay, so let's rewrite that. Y prime is going to equal negative 3x squared plus 12x minus 15. And then over here, right next to it, I'm going to do the double prime, which is going to be negative 6x plus 12. Okay, so I'm going to put 0 in. So 0 is going to equal, I'm going to factor out negative 3. That's going to leave me with x squared minus 4x plus 5. And then this can't be factored, so it does not factor. So that means there's no maximums or minimums for this particular function. Now the second derivative, so when I set that equal to 0, we'll have negative 6x plus 12. So 6x equals 12. So that means x is equal to 2. So that means there's inflection at x equals 2. All right, so we're going to figure out what y is when x is equal to 2. So we'll have negative bracket, we're substituting in, so 2 cubed plus 6 times 2 squared minus 15 multiplied by 2. So we get negative 8 plus 24 minus 30. So that's going to give us a value of, that's negative, so that's 16, take away 30 is negative 14. So therefore, the point has the coordinates 2, negative 14. So in terms of sketching a graph, we have this information. Right now, what we want to do is we're going to create another type of interval table. So I'm going to do f double prime of x, and then the function itself. And really, we only have to worry about 2 intervals. So we need to do when x is less than 2 and when x is greater than 2, because we want to know what's happening before and afterwards. So this right here is my second derivative. So that's what I'm substituting in. So if I were to take 1 and substitute in, we'd get a positive, which means that it's concave up. If I have x is greater than 2, so that's going to give me a value of a negative, so it's going to be concave down. So that gives us a lot of information in terms of what's happening. So right now, to do a really quick sketch, I have enough information. I'm going to need to extend this page down though, because that y value of my inflection is at negative 14. So x is 2, negative 14. I have my value here. The first derivative has no value, so there's no minimums or maximum. Now it's telling me that it's concave up prior to this value and concave down afterwards. So because it's a cubic function, I know that it's going to be concave up and then switching to concave down. Right now, there's other values that we possibly know right here. I'm probably off. Actually, I'm definitely off because when I look very quickly, I can tell that there's an x and y intercept at 0, 0 because of the nature of the function. So I'm just going to fix that. Okay. Because even though it's a sketch, you still have some values that you know. So it's concave up, switching to concave down. No minimums or maximum, only a point of inflection. So mathematically, all we're doing is figuring out when the second derivative has a value of 0 and analyzing before that value of x and after that value of x. All right, so we're back to this equation that we had before. We found an equation similar to this when we were looking at whether or not a minimum or maximum occurred. So right now, for this function, it says sketch the graph. I'm going to go through and figure out some stuff. So right away, when I look at it, my domain is going to be x is an element of the reals. The range is going to be y is an element of the reals, such that y is going to be greater than or equal to 0. This squared right here, that's in that exponent. That's the value that's telling me that it's always going to be positive. Okay, so f prime of x is going to equal 2 over 3 x to the power of 1 over 3. So now all of a sudden there's no zeros. So we have 0 over 2, 3 to the x, 1 over 3. 0 does not equal 2. Okay, so based on that, it looks like there's no critical point. However, we need to remember x equals 0. Okay, so now I'm going to rewrite my first derivative. So f prime of x is equal to 2 over 3. I'm going to write it like this as negative 1 over 3 like that. To do the second derivative, we will get negative 2 over 9 x to the negative 4 over 3. So when we're solving, we'll have negative 2 over 9x to the 4 over 3. Once again, 0 does not equal negative 2. But consider x equals 0. Because now all of a sudden there's a restriction in this denominator for that particular derivative. So I'm going to do a little interval table. So I just need to consider values that are less than 0 and x is greater than 0. So f double prime of x. Then we can also include f prime of x because it was a critical value from the first derivative. And then finally, we have the final function that we can analyze. Okay, so first derivative was 2 over 3 x to the 1/3 in the denominator. So if I pick a negative value in the first derivative, it's negative, which means we're going to be decreasing. If I take a value that's less than 0 and substitute it into this expression right here, we are going to have a negative as well. So that means that it's concave down and it's decreasing. Now if we do the same thing and substitute in a value greater than 0 into the first derivative, I'm going to get a value that's positive, which means it's going to be increasing. And then if I substitute into this value over here, I am going to get a negative once again, which means that it's still concave down. So now, how do I translate that into a picture? All right, so the only point that we have is at 0, 0. Now before that value, it's concave down because the second derivative is less than 0, and it's decreasing. So this is one of those graphs that kind of look like the bird. Okay, And then over here, it's still concave down, but it's increasing. So the second derivative gives us a little bit more information regarding what the curve is going to look like. So we did an example similar to this in 4.2 where we ended up with a minimum value, which once again we still have. There's no point of inflection in this case. However, at 0, 0, the inflection is staying the same. All right, so I guess if we were to summarize what this lesson is meant to show you is that using the second derivative, it tells us what the curvature of the curve is like. So if it's concave down, think of it as a frown. And if it's a concave up, if someone is up, they're generally happy. So you can think of it that way. When I get back on well, I guess it'll be Friday since you have the retreat tomorrow, we'll definitely go over this in more detail and we'll start looking at asymptotes.